Imagine this. Every time you tap to stream your favorite show, transfer money, or even just log into your student portal here at Tarleton, you're not just interacting with an app or a website. What if I told you that beneath every single one of those actions, there's a highly precise, often silent, conversation happening with a database? Billions of times a day, these hidden architects shape almost every digital interaction you have.
It's absolutely true. The digital world doesn't run on magic. It runs on meticulously organized databases. And for anyone looking to truly understand, design, or secure the digital infrastructure of tomorrow, especially our students in the Dr. Sam Pack College of Business, learning to master these systems starts right here. These aren't just abstract concepts. They are the foundational skills for success in business, technology, and, well, beyond. Understanding them is your shortcut to building the future.
So if you're curious about these hidden architects of our digital lives, you've definitely found the right place. Before we dive in, please be sure to follow and share this deep dive with anyone who wants to go behind the data. And check the episode description for additional resources, because we're about to unpack some truly foundational and, frankly, fascinating concepts today. Our mission for this deep dive is to explore the very heart of how data is organized, the relational model. We'll trace its origins, dissect its core components, learn the essential rules that keep data reliable, discover how to clean up messy data through normalization, and even understand how these systems actually communicate and manage themselves behind the scenes. Think of this as your essential guide to the design, development, and implementation of robust databases.
Exactly. Let's get into it. Okay, so before 1970, the world of databases was incredibly fragile, almost like a house built on quicksand. Systems relied on what we called physical data models. Picture a student record physically pointing to where their grades were stored on a disk.
Like a literal address.
Pretty much, yeah, like a physical chain directly connecting two documents in a filing cabinet. So if you ever moved that student file or maybe just added a new piece of information, those physical pointers could break.
I see. And then everything falls apart.
Exactly. Your entire database structure could collapse. It was rigid, inflexible, and maintaining or extending these systems was a constant nightmare.
Okay, so that sounds like a huge pain point. And this is where the entire landscape shifted. In 1970, an IBM researcher named Edgar F. Codd introduced a concept that completely revolutionized data management. He unveiled the relational model, and its brilliance came from grounding data management in rigorous mathematics.
Yeah.
Specifically, set theory and predicate logic.
Right.
This wasn't about fragile physical links anymore. It was about pure logical connections.
Precisely. Codd's breakthrough was understanding that instead of those problematic physical pointers, relationships between data could be represented simply by values.
Values, like shared numbers or codes.
Exactly. Common keys shared between tables. This concept, known as logical data independence, was a game changer. It means your applications, the ones you interact with every day, don't need to care how the data is physically stored on a drive.
Okay.
They just focus on the logical connections, the relationships between different pieces of information. The underlying physical storage could change, be optimized, or even move entirely, and your applications wouldn't break a sweat.
Wow. That is a big deal. It was a liberation for developers, I imagine.
Oh, absolutely, and a giant leap for data reliability.
And that liberation, that elegant logical foundation that paved the way for the powerful, high-level query languages we use every day, like SQL-structured query language.
That's right.
Instead of painstakingly navigating physical paths, suddenly you could ask complex questions of your data in a human-readable way, making data manipulation incredibly flexible and accessible.
The relational model quickly came to dominate for very compelling reasons. It brought an unprecedented level of simplicity, flexibility, and mathematical rigor to data management. Database design became more intuitive, querying became powerful, yet straightforward.
Easier to extend, too, I bet.
Dramatically simplified extending systems to meet new business needs, yes. And critically, it significantly improved data integrity by allowing clear, logical rules and constraints to be applied across your data. Today, whether you're working with Oracle, MySQL, SQL Server, or PostgreSQL, the relational model forms the fundamental backbone. For anyone in modern organizations, particularly students aiming for careers in business and technology, understanding this model isn't just academic, it's absolutely fundamental to designing effective and reliable database systems.
So it's not just theory, it's practical skill number one. Okay, so how does this revolutionary model actually structure our information? Let's get into the nuts and bolts. At its core, data in a relational database is organized into tables, which we also call relations.
Right. Think of them not just as spreadsheets, but as super-powered, highly disciplined data containers.
Okay.
Each table has a unique name and is perceived as a two-dimensional structure. It holds homogeneous tuples,
Homogeneous tuples, meaning,
meaning every single row in, say, a student's table is, well, a student record, not a mix of student records and, I don't know, car records.
gotcha, all the same type of thing.
Exactly. And the order of rows doesn't matter, and critically, you can't have two exact duplicate rows.
Okay, rows. Each row, also known as a tuple or record, represents a single complete entry in the table, one instance of an entity. So in our students table, one tuple holds all the info for a single student.
Correct. And like rows, the order of the attributes, the columns within a tuple is irrelevant to the model itself, but each tuple must be unique.
Then we have the columns, or attributes, sometimes referred to as fields.
Mm-hmm.
This is a specific property of the entity, like a student's last name or date of birth.
Right. Each column has a unique name within its table, and just like rows, their sequence isn't important to the relational model itself, though we arrange them for clarity.
And crucially, each attribute also has a domain. What's that about?
The domain is simply the set of all possible valid values for that attribute. For instance, an age attribute might have a domain defined as positive integers between 0 and 120.
So it enforces rules on the data type and range.
Exactly. This isn't just a detail, it's a vital rule that ensures values entered into that column are of the expected type and fall within an acceptable range. It prevents garbage data from sneaking in.
Very important. And finally, we encounter null values. This isn't zero.
No, definitely not 0 or an empty string. It's a special marker for no value or unknown. Think of it as a box with a giant question mark inside, signaling we don't know or not applicable.
Okay.
This distinction is critical because it accurately represents missing or undefined information, which Codd himself explored extensively with multi-valued logic in extensions to his model.
Fascinating. So there's logic behind even the unknown.
Absolutely.
Right.
Now, behind these core concepts, the relational database operates with a distinct layered architecture. At the highest level is the database schema. Think of this as the comprehensive blueprint, the master plan for the entire database.
The overall structure.
Right. It meticulously defines the structure of all your tables, the fields they contain, the relationships that link them, and even other objects like views and indexes. It's the logical design that tells us what data we store and how it's all organized. It serves as your guide for data modeling, hitting that KO2 outcome.
Okay, the blueprint, what's under that?
Beneath that, acting as the central processing unit, is the relational engine. This is the brain of the DBMS, the component that processes every single SQL query you submit.
So when I ask for data,
Exactly. When you ask the database for information, the relational engine interprets your SQL commands, breaks them down, translates them into the actual operations needed to retrieve or manipulate that data. It handles query parsing, validation, and most importantly, it optimizes the query for the fastest possible execution.
the smart part and
Yeah.
the physical part.
And finally, managing the physical foundation is the storage engine. This component is the workhorse. It's solely responsible for how data is physically stored, organized, and retrieved from the disk.
The bits and bytes level.
Precisely. It manages file systems, indexes, ensures efficient input-output operations. It completely abstracts away those messy details, allowing the relational engine and, by extension, your applications to focus purely on the logical structure.
Schema. Relational engine, storage engine. Got it. Hashtag tag check C. Why choose relational?
Yeah.
Advantages and challenges. With that intricate structure, it's crystal clear why the relational model became the undisputed heavyweight champion of data management. For modern organizations, its advantages are immense, directly addressing our knowledge outcomes like KO1 and KO4, and skills outcomes like SO3. Top of the list is truly powerful data integrity and reliability.
Absolutely crucial.
Through a rigorous set of rules, constraints, and defined relationships, relational databases ensure accuracy and consistency. Remember the ACD properties, atomicity, consistency, isolation, and durability.
The gold standard for transactions.
These are the ironclad guarantees that your transactions, whether transferring money or enrolling in a course, are processed reliably and accurately every single time. That's a huge aha moment for anyone dealing with critical data.
It really is. Peace of mind.
Then there's the incredible ease of use and flexibility. SQL, the standard language, is surprisingly intuitive, right?
Relatively speaking, yes. It makes database management accessible to millions. And it's incredibly versatile. It powers everything from small business apps to global e-commerce platforms.
And security's baked in.
Robust features, yeah.
Yeah.
User authentication, granular access controls. You can precisely dictate who sees what, who can make changes, down to individual columns. Very important.
They also offer impressive scalability. They can handle growing data and users.
Yes, capable of handling ever-increasing amounts, often through both vertical scaling, meaning more powerful hardware, and horizontal scaling, distributing data.
The standardization around SQL is a huge benefit too, isn't it?
Yeah.
Skills are transferable.
Definitely. Learn it once, apply it many places. Makes you a more valuable professional.
And thanks to techniques like normalization, which we'll explore soon, they excel at data redundancy elimination.
Right. Less duplication means less storage, fewer chances for data inconsistencies, cleaner, more trustworthy data.
Okay, sounds great, but it can't be all sunshine and roses. What are the hurdles?
But of course, no solution is without its complexities, and recognizing these challenges is crucial for effectively evaluating DBMS functions and architectures, that KO4 outcome again. While powerful, managing truly large, intricate relational databases can be surprisingly complex.
Especially with lots of tables.
Particularly when you're dealing with dozens or hundreds of tables that need to be joined together for complex queries. It's like trying to untangle 1,000 strands of spaghetti while they're all cooking at once. It can quickly become an administrative and development hurdle.
Okay, I can picture that. What about speed?
Performance can also degrade, especially with truly colossal data volumes or when running highly complex analytical queries that touch many parts of the database. Query optimization in these scenarios becomes a specialized art form.
And the rigid schema, you mentioned that earlier.
It can be a double-edged sword. While it enforces structure beautifully, making significant changes to that schema in a large operational system can be difficult and disruptive.
Downtime, maybe.
Sometimes requires extensive planning and downtime, yes. Also, relational databases are primarily built for structured tabular data. They offer more limited native support for unstructured data types like documents, images, or JSON, often requires workarounds.
What about spreading the load, scaling out?
And while they can scale, scalability in distributed systems for traditional relational databases, particularly horizontal scaling, has historically been more challenging compared to some newer NoSQL alternatives. It's an active area of innovation, but it's a known hurdle designers grapple with.
Okay, and one last thing, the overhead from normalization.
Right. While vital for integrity, normalization splits data into many smaller tables. This often means you need to perform multiple joins to reconstruct the full picture for a query. This adds processing overhead and can impact performance.
So the trade-off.
A constant trade-off database designers weigh, absolutely.
So where do you actually see this power in action? You said everywhere.
Pretty much everywhere. Relational databases are the silent workhorses powering almost every digital system you interact with daily. In business applications, they are absolutely foundational.
Like inventory.
Think about a university's inventory management system, tracking every textbook, every piece of lab equipment, its quantity, location, usage history, all that detail.
Yeah.
Or CRM, customer relationship management systems, like those used by our Dr. Sam Pak College of Business to track alumni interactions and support.
Storing every touch point, preference, detail about customers or constituents.
Exactly. And ERP, Enterprise Resource Planning Systems, integrating all aspects of an organization's operations, finance, HR, all built on a robust relational backbone.
Okay, that makes sense for business. What about specific industries?
In industry examples, their presence is just as pervasive. Banking relies heavily on them for managing transaction histories, account balances, customer details with unyielding accuracy.
Can't mess that up.
Definitely not. Healthcare systems use them to meticulously safeguard patient data, manage appointments, track medical records with precision. In telecommunications, they handle vast customer records and billing information for millions of subscribers.
And e-commerce, like Amazon.
And of course, e-commerce, like when Amazon fulfills an order, uses incredibly sophisticated relational databases. They manage product catalogs, process customer orders, track shipping details, update inventory in real time across the globe. It's a massive operation.
And right here at home are university systems at Tarleton State University.
Running on these same principles, yes. Your student enrollment, the course catalogs you browse, grade tracking, managing your student IDs, library records.
All databases.
All underpinned by relational databases. They are tirelessly working to ensure your academic journey runs smoothly. showing you that these aren't just abstract ideas. They are the concrete systems enabling your daily digital life, and mastering them opens doors to countless career paths, addressing that KO1 outcome directly. Okay, let's talk about keys. Keys are not just identifiers, they are truly the bedrock of the relational model. Think of them as the DNA of your data. Absolutely fundamental.
The DNA, I like that.
They are the mechanisms that ensure data integrity, guarantee uniqueness for each record, and enable incredibly efficient access and retrieval. Without them, trying to manage vast data sets and execute complex queries would be an incredibly inefficient and error-prone endeavor.
Chaos. Basically trying to find one student without an ID.
Pure chaos. Or linking an order to its customer without a shared identifier. Impossible. So first and foremost, keys provide uniqueness. They ensure that each individual record in a table is distinct and uniquely identifiable. Paramount for maintaining data accuracy. You don't want two identical student records causing confusion.
Right. And they help with integrity, too.
Secondly, yes, crucial for data integrity. By preventing duplication and ensuring distinct records, keys maintain consistency across the entire database, prevents contradictory information.
And finding stuff faster.
And finally, keys facilitate efficient data retrieval. They are the essential mechanisms we use to define relationships between tables, allowing the database to quickly navigate and find related information, vital for faster querying and optimal data organization, directly supporting our writing and communication outcome, WO1, by enabling clear, accurate data representation.
Uniqueness, integrity, efficient retrieval. Got it. Keys are critical.
Yeah.
Hashtag tag B superkeys. Decoding key types. Okay, let's unpack these different types of keys that act as our data's unique fingerprints. Let's start with superkey. What's that?
A superkey is actually a very broad concept. It's any attribute or set of attributes that can uniquely identify a row in a table.
Any set, even if it has extra stuff.
It can include extra attributes that aren't strictly needed for uniqueness, but it still gets the job done. For example, in an employee table with empid, emp number, and emp name, the set empid, emp number, emp name is a superkey. But so is just emp alone if empid by itself is unique.
Okay, so superkeys are broad. How about candidate key?
Building on that, a candidate key is where we get more precise. It's a minimal superkey.
Minimal meaning.
Meaning it uniquely identifies a record, but without any unnecessary or redundant attributes. You can't remove any attribute from a candidate key and still guarantee uniqueness.
The bare minimum for uniqueness.
Exactly. Every table needs at least one, and a table can certainly have several. So, returning to our employee table, if both empid and emp number are independently unique identifiers for an employee, then empid and emp number are both valid candidate keys.
Okay, multiple possibilities. And this is the moment everything shifts. From that pool of candidate keys, one is chosen to be the primary key, PK.
That's the one.
This is the main official unique identifier for the table, the one you'll use most often to refer to a specific record. It has two absolutely crucial rules, right? The entity integrity rule.
Correct. Must be unique and cannot contain NUL values.
Why no NELs?
If a primary key were NUL, how could we possibly identify that row uniquely? It would be a ghost record. Every record needs a clear identity.
Makes sense. And sometimes you need more than one column.
Sometimes, yes. No single attribute is unique enough, so a combination of two or more attributes forms what we call a composite primary key. A classic example is student ID, course ID for an enrollment table. The combination uniquely identifies a specific student's enrollment in a specific course.
Okay, primary key chosen. What happens to the other candidate keys?
Any candidate key that wasn't chosen as the primary key becomes an alternate key. These keys still possess the power to uniquely identify records, but they aren't the designated primary key.
So they're like backup identifiers.
Kind of. If empid was chosen as the primary key for our employee table, then emp number, if it's also a unique candidate key, would become an alternate key. You could still use it to find records.
Gotcha. This raises an important, very practical question for database designers. Should a key have real-world meaning? This is surrogate keys versus natural keys.
Exactly, a big design choice.
A surrogate key is artificial, right? System-generated.
Yes, an artificial system-generated identifier with no real-world meaning. Think of an auto-incrementing course ID. It's just a number the system creates to uniquely identify a record.
Like a social security number just for the data itself.
Sort of, yeah. And it's incredibly handy when natural keys are complex, might change, or might not always be available.
And a natural key or external key?
That's an attribute that does have real-world meaning and is used as a primary key. Examples include a social security number, an ISBN for a book, or maybe a student's campus ID.
Seems more readable.
Can be more readable, but they can pose challenges if their values change over time or if unexpected collisions occur.
So surrogate keys are often safer.
Often the pragmatic choice in modern database design, yes, more stable. Now, connecting these building blocks is where the real power of relational databases shines. And this brings us to foreign keys, FK.
This is the magic part. Linking tables.
This is truly where the magic happens. A foreign key is an attribute, or a set of attributes, in one table that references the primary key of another table, what we call the parent table.
Okay.
This mechanism establishes those crucial parent-child relationships, seamlessly linking data across different tables. For example, imagine an orders table. The customer ID in this table would be a foreign key.
And it points back to the main customers table.
Precisely. It would reference the customer ID primary key in the customers table. This simple yet powerful link ensures every order is correctly tied to an existing customer, maintaining what we call referential integrity, hitting KO3 and WO1 outcomes.
Okay, linking different tables. Can they link within the same table?
What's fascinating here is that foreign keys can even be self-referential. This is when a foreign key references the primary key within the same table.
Huh. Why would you do that?
It's a clever way to capture hierarchical relationships like an organizational chart. In an employee table, you might have an employee ID as the primary key, and then a manager ID attribute, which is a foreign key also referencing employee ID.
So manager ID points to another employee ID who's a manager.
Exactly. This links an employee directly to their manager within the same table, allowing you to build out complex reporting structures efficiently.
What if they don't have a manager, like the CEO?
If a manager ID is NULL, it signifies an employee at the top, like a CEO, with no manager above them.
Cool. So the way tables link defines how they interact. There are different types of relationships we commonly encounter, right? Part of data modeling, KO2, WO1.
Correct. 3 main types.
The simplest is 1-to-1, 1.1.
Right.
One record matches one record.
Yes. One record in Table A matches exactly one record in Table B. For instance, an employee and their unique employee profile information might be split into 2 tables, but linked 1.1.
Maybe for security or optional data.
Could be, yes. Or to manage optional attributes more cleanly.
Okay. The most common is one-to-many, 1M, you said.
By far the most common and often the most crucial. Here, one record in Table A can match many records in Table B. A classic example is one customer placing many orders.
Customers are the one, orders are the many.
Exactly. The customer re in the customers table is the one, and many rows in the orders table can share that same customer ID as a foreign key, making it the many. This is the bread and butter of relational design.
Okay. And the tricky one, many-to-many, MN.
Right. This is when records in Table A can relate to multiple records in Table B and vice versa.
Like students and courses. A student takes many courses, a course has many students.
Perfect example. You can't directly represent this with just a foreign key in one table. Instead, these relationships are typically managed by introducing a separate intermediary table, often called a junction or associative table.
Table in the middle.
Exactly. In our student course example, this would be an enrollments table. It would contain foreign keys for both student ID and course ID, effectively breaking the MN into 2 1M relationships.
And that table would store the grade.
Usually, yes. The enrollments table would uniquely record each instance of a student taking a particular course and often store attributes unique to that relationship, like a grade or semester. Okay, moving on. Integrity constraints are truly the unsung heroes of data quality in any relational database.
The rules of the road.
Think of them as the unbreakable laws of your data kingdom. They are a robust set of rules embedded within a database management system, specifically designed to ensure that the data stored is always accurate, consistent, and supremely reliable.
So they prevent mistakes.
Their primary role is to prevent mistakes, invalid entries, broken relationships, or data that simply doesn't make sense within the logical structure of your database. They are established when the database schema is defined and are rigorously checked every time data is modified. Insert, update, delete.
What's the main goal?
The fundamental purpose of these constraints is to maintain that high level of data quality. They ensure data is always meaningful, adheres to its logical structure, and that crucial connections remain valid and unbroken.
Okay, and you mentioned legal instances.
Right. A legal instance is any state of the database where all defined constraints are satisfied. The DBMS actively works to prevent any operation that would lead to an illegal instance.
Like adding an order for a customer who doesn't exist.
Exactly. It prevents that, safeguarding your data's integrity. This rigorous enforcement helps avoid data entry errors and ensures the stored data is a faithful representation of real-world meaning. #tag_B. Diving into constraint types.
Okay, let's dive into the specific types of integrity constraints, KO3, SO3. First up, domain constraints. What are those?
These rules define exactly what kind of data is allowed in a particular column or attribute, setting clear boundaries for the values.
Like data types, integer, string, date.
Yes, enforcing specific data types is key. A date of birth column won't accept hello. Beyond basic types, we have the not NLL constraint. Pretty straightforward.
Ensures the column can't be empty or unknown, like a student name.
Correct. Then there's the check constraint, which validates data against a specified condition.
Like age between 18 and 30.
Or salary 0. You could use it for formats too. Imagine a student-ID column at Tarleton enforcing a specific 21 CSE #tag format.
Or a semester column only allowing fall, spring, summer.
Precisely. These constraints are vital for preventing invalid or inconsistent data from ever entering your database. Makes it far more reliable.
Next, entity integrity constraints. This is about the primary key again.
Absolutely critical, yes. It directly impacts how we uniquely identify records. This rule states the primary key cannot contain NLL values and must be unique.
We covered why. Can't identify a row if the PK is NELL.
Exactly. Every record must have a clear, unambiguous identity. So a studented PK column cannot have a NLL value in any row. Ensures every student record is always identifiable.
Building on that, key constraints more broadly enforce uniqueness. The primary key constraint we know. What about the unique key constraint?
This ensures that all values in a specified column or group of columns are distinct.
How is it different from a primary key?
The key difference is that a unique key can allow one NULL value.
Ah, okay, like maybe an email address.
Perfect example. An email column in an employee table is a great candidate. You wouldn't want two employees with the same email, but you might have one employee whose email is currently unknown. The single NUL allows for that.
Got it. Now, referential integrity constraints. These maintain relationships between tables.
Exactly. All about the links. The core foreign key rule dictates that a foreign key in one table must either match an existing primary key value in the reference parent table or be NULL.
This prevents orphan records, child records pointing to nothing.
Yes, prevents those dangling references. Imagine an order record for a customer ease that no longer exists in your customer's table. Referential integrity prevents that. Ensures every child has a valid parent.
What happens if you try to break the rule, like delete a parent record?
When a violation occurs, the DBMS can be configured to take specific actions. It can simply reject the action and demerit implementation, or cascade the deletion or update to all related child records on delete cascade.
So deleting a customer deletes their orders.
Potentially, if set up that way. Or it could set the foreign keys in the child table to null on delete set null, or a default value on update set default. For example, an orders table's customer E FK must exist in the customer's table's customer A PK, or BNL, ensures every order is tied to a real customer.
Okay, those seem fundamental. What about more advanced constraints? Assertion.
An assertion is a truly global integrity constraint. Unlike column checks, assertions apply across multiple tables or even the entire database, ensuring a specific condition is always met. In SQL 92, you define it with create assertion name, check predicate.
Give me an example.
A classic from banking. Ensuring the total loan amount issued at a branch is always less than the total account balances held at that same branch.
Ah, prevents a branch from lending more money than it has deposits.
Exactly. A vital business rule enforced at the very core of the database.
Powerful stuff. And then triggers.
And then we have triggers. These are powerful procedural statements that automatically execute in response to specific events happening in the database. Insert, update, delete operations.
So they react to changes automatically.
Yes. Triggers are incredibly useful for enforcing complex integrity constraints or implementing sophisticated business rules that standard declarative constraints can't handle alone. For example, you could have an after update trigger on an account table. If an account balance goes negative after an update,
The trigger could maybe turn it into a loan.
Precisely. It could automatically convert that negative amount into a loan, reset the account balance to 0, and then insert a new record into a separate loan table. allows for dynamic, automated reactions to data changes, maintaining complex business logic directly within the database itself.
Very cool. Lots of ways to keep data clean and consistent. So we've laid down the rules, the constraints, but how do we diagnose a bad database design in the first place? Where do things go wrong?
It often starts with understanding functional dependencies.
Okay, functional dependencies or FDs. What's the core idea?
It's a formal way to express something quite intuitive. If you know X, you can determine Y. This means that if two rows in a table have the same value for attribute set X, they must also have the same value for attribute set Y.
Okay, X determines Y. X is the determinant. Y is dependent.
Exactly.
Give me an example.
Okay, manufacturer state. Knowing the manufacturer's ID tells you their state. You don't need any other information.
Right, or in a university context.
Student ID, course ID, grade. A specific student in a specific course can only ever have one grade. Knowing both student and course tells you the grade.
So why are these FDs so important?
Functional dependencies are absolutely crucial because they allow us to formalize the inherent facts and relationships within our data. They are the foundational building blocks for understanding and correctly applying database normalization, hitting KO2 and WO1 again.
The database's conscience, you said, preventing data lies.
Exactly. They guide us in ensuring that non-key attributes in our tables depend on the key, the whole key, and nothing but the key.
Catchy phrase. What does it mean?
It encapsulates the essence of good database design, ensures each piece of information is stored in the most logical, non-redundant place. Without a clear understanding of FDs, attempting to normalize a database would be, well, a shot in the dark.
Leading to flawed designs and anomalies.
Precisely. Painful data anomalies.
And what happens when we ignore those functional dependencies and design our databases poorly? That's when we encounter data anomalies.
Yes, these are undesirable side effects or inconsistencies that crop up during routine database operations. Insert, delete, update.
When the database is messy, basically.
Yeah.
Unnormalized.
Right. It's like a messy room that causes problems every time you try to find something or add something new.
What causes them?
Typically common design flaws. Lumping unrelated data together, failing to properly separate different conceptual entities, or allowing unwanted functional dependencies. For instance, an attribute might depend on only part of a composite key or even on another non-key attribute. Leads to problems.
3 main types, you said.
Yes, each with significant real-world impact. Can lead to corrupted data, bad business decisions.
Okay, what's the first one?
The first type is the insertion anomaly. This makes it difficult or even impossible to insert new, valid data into your database. Imagine an enrollments table that tries to store everything. Student ID, student name, course name, instructor.
Okay, one big table.
Now, if a new course is created but doesn't have any students enrolled yet, you literally can't add that course's information to this table.
Why not?
Because student ID would likely be part of the primary key. It would be required. You'd be forced to create a dummy enrollment just to store the course info.
Oh, that's bad data.
Clearly undesirable, pollutes your data. This design inappropriately ties the existence of a course to its enrollment, creating this anomaly.
Okay, that's insertion anomaly. Next up is the deletion anomaly. This is when deleting one piece of data causes the unintended loss of other important, unrelated data.
Ouch. Losing data you didn't mean to lose.
Let's stick with that problematic enrollments table. If the very last student drops a course and you delete their enrollment record,
Uh-oh.
you might inadvertently also delete the only copy of the course name and instructor information for that course. You wanted to remove an enrollment, not erase the course details from existence.
That could be catastrophic for critical information. Bad news.
And the third one? Update anomaly.
And finally, we have the update anomaly. This leads to inconsistencies that arise from partial updates when data is duplicated unnecessarily. If, in our enrollments table, the instructor name for a course is stored repeatedly in every row for each student in that class.
So the instructor's name is there like 30 times if there are 30 students.
Exactly. And the instructor's name changes. You'd have to update every single one of those 30 records. If you miss even one, your database ends up with conflicting, inconsistent data. Some students link to the old name, others to the new.
A nightmare for data accuracy and reliability.
Absolutely. Leads to untrustworthy reports and bad decisions. These anomalies are clear signals that your database design needs some serious reorganization.
Which brings us to Normalization.
Exactly.
The solution to these data nightmares, these insertion, deletion, and update anomalies, is normalization.
The cleanup process.
It's like Marie Kondo for your data, systematic step-by-step process of reorganizing a relational schema to minimize redundancy and fix those pesky dependency issues we just talked about.
Right. Essentially, normalization transforms a problematic, anomaly-prone schema into an equivalent one that has no update anomalies,
Making data clean, efficient, robust.
ensuring it serves as a reliable foundation for all your business operations.
It's hierarchical, right? You build up through levels.
Yes, it follows a hierarchical approach. Normal forms build on each other. To achieve a higher normal form, a table must first satisfy all the conditions of the lower normal forms. The most commonly addressed and practically important ones are first, second, third, and sometimes boys cod, BCNF, and fourth normal form.
Okay, let's walk through them.
The journey to clean data, applying these data modeling techniques, KO2, SO2, begins with first normal form, 1NF. The core condition here is that every attribute value must be atomic.
Atomic meaning indivisible, one value per cell.
Exactly. You cannot have repeating groups or lists within a single cell. Any properly defined table in the relational model, by its very nature, is in 1NF because the model itself doesn't allow multi-valued attributes in a single field.
So what's a violation look like?
A common violation example would be a phone number's attribute storing 817-555-1234, 214-555-5678 in one field. That's two phone numbers.
Or columns like item 1, item 2, item 3.
Exactly. That shows repeating groups of item data, like trying to cram multiple pieces of info into one drawer.
So how do you fix it?
The solution to a 1NF violation is typically to create separate tables for those multi-valued attributes. For phone numbers, you might have a student funds table linking back to student, with each phone number getting its own row. Or if the number of values is fixed and small, maybe separate attributes like home phone, cell phone.
Okay, goal is one atomic value per cell. What's next? Second normal form, 2NF.
Moving on, second normal form 2NF addresses a crucial issue for tables with composite primary keys.
Keys made of multiple columns.
Right. For a table to be in 2NF, it must first be in 1NF, and every non-key attribute must be fully dependent on the entire primary key, not just a part of it.
No partial dependencies. Everything depends on the whole key.
Exactly. Like saying every part of a puzzle piece only makes sense when connected to the whole puzzle, not just one corner.
Give me a violation example.
Let's illustrate. Imagine an enrollment table. Student ID, course ID, student name, course credits, grade. The composite PK is student ID, course side. Grade depends on both student ID and course side. A specific student in a specific course gets one grade. That's fine.
But student name only depends on student ID.
Correct. And course credits only depends on course side. These are partial dependencies because they depend on only part of the composite primary key, creates redundancy.
So the solution is to break it up.
The solution involves decomposing the table. We'd move StudiGame to its own student table, keyed by student ID. Similarly, course credits would go into a course table keyed by course side. The enrollment table then just contains student ID, course ID, grade.
Ah, much cleaner. Grade depends on the whole key in enrollment, and the other stuff is where it belongs.
Precisely. Eliminates the partial dependencies.
Okay, 1NF, 2NF.
Well,
What's third normal form, 3NF?
the next step is third normal form, 3NF. A table is in 3NF if it's already in 2NF, and no non-key attribute is transitively dependent on the primary key.
Transitively dependent, what does that mean?
It means a non-key attribute, let's call it Z, depends on another non-key attribute, Y, which in turn depends on the primary key, X. So you have XY and YZ implying XZ, but indirectly.
Okay, so a non-key attribute depends on another non-key attribute.
Basically, yes. In simpler terms, every non-key attribute must directly depend only on the primary key and nothing else. It's about ensuring every fact is a direct fact about the key, not a fact about another non-key fact.
Example time.
Consider this violation example. An employee table with empid, epname, dept phone. Empid is the primary key. We know empid dept employee belongs to one department, but we also likely know dept a dependency. Each department has one phone number.
Ah, so empid determines dept, and dept determines dept phone. That's the transitive dependency. Empty dept phone through dept.
Exactly. Dept phone isn't a direct fact about the employee. It's a fact about the department. Storing it in employee introduces redundancy.
And update anomalies, right, if the department phone changes.
You'd have to update it for every employee in that department. Classic update anomaly.
So the solution?
Factor out the transitive dependency. Create a separate department table with dept phone. Then the employee table only keeps empid, empname, dept, with dept acting as a foreign key to the new department table.
Breaks the chain. Now, everything in employee depends directly on MPED.
Correct. Much better design.
Okay, 3NF seems pretty solid. Is there more? You mentioned Boyce-Codd normal form, BCNF.
Yeah.
3.5NF.
Now, for those really digging deep into database design, there's Boyce-Codd normal form, BCNF. It's a stricter version of 3NF. The condition here is that for every functional dependency X or Y, X must be a superkey.
A superkey, meaning it identifies the row, possibly with extra attributes.
Right. Or Y must be a subset of X, which is a trivial dependency we don't worry about. BCNF aims to eliminate all redundancy based on functional dependencies.
Why does it matter if 3NF often suffices? Is this common?
For 90% of you building standard operational systems, 3NF is usually enough. But BCNF handles those rare cases where a 3NF table still has multiple overlapping candidate keys and, despite being in 3NF, can still suffer anomalies.
Overlapping candidate keys. Tricky stuff.
It can be. For example, imagine a today's court bookings table where rate type determines court, rate type a court. But rate type itself isn't a superkey for the whole table. Maybe court start time is the primary key. If a specific rate type should only ever apply to a single court, like saver only for court 1, storing this dependency, rate type court, within the booking table when rate type isn't a key can lead to redundant court information or update issues.
So how do you fix that with BCNF?
The solution in such a case is to decompose the table favor. You'd split it into a rate types table, which has rate type as a key, along with court and maybe member flag, and a today's bookings table, with court start time, end time, member flag. Now, both new tables are in BCNF, eliminating that specific type of redundancy. So if you're building complex systems with overlapping candidate keys, BCNF becomes your crucial next step.
Okay, that's definitely advanced. And finally, fourth normal form, 4NF. This tackles something different.
And finally, we reach fourth normal form, 4NF, which tackles a completely different beast, multi-value dependencies, MVDs. A table must be in BCNF, and if there are non-trivial multi-value dependencies, it must be decomposed.
Multi-value dependency, what's that?
An MVD exists when two attributes are independent of each other, but both depend on a third attribute, typically the primary key. This structure leads to unnecessary combinations of values being stored. It's ensuring that a table doesn't accidentally try to model two or more independent one-to-many relationships at the same time.
Like storing hobbies and favorite foods together, even if unrelated.
Kind of like that, yes. Let's use a classic violation example. Professor, profit, course taught, committee assignment. Suppose a professor can teach multiple courses and serve on multiple committees, and these two sets of facts are entirely independent.
Okay. Smith teaches CS 101, CS 202, CS 303, and is on the curriculum and hiring committees.
Right. If Professor Smith teaches 3 courses and is on 2 committees, an unnormalized table might store all 3 by 2 equals 6 combinations of profit, course taught, committee assignment rows, repeating profit and the courses committees unnecessarily. Massive redundancy because a specific course has nothing to do with a specific committee here.
So the solution is to split it.
Simple. Split the table into 2. One for professor courses, profit, course taught, and another for professor committees, profit, committee assignment. Now, each table focuses on a single independent fact, eliminating the multi-valued dependency. Makes the data much cleaner without those artificial combinations.
So for most people, 3NF or maybe BCNF is the goal.
For the majority of you, yes, 3NF or BCNF will be sufficient. But for advanced academic or specialized data modeling, 4NF is key. Connecting all this theory to practice, the overarching benefits of proper normalization hitting KO2, SO2, and WO1 are profound. It leads to incredibly robust schemas by ensuring data integrity, providing essential flexibility to insert and delete data without anomalies, and supporting scalability by significantly reducing redundancy.
Building a database that lasts.
Exactly. Stands the test of time and changing business needs. Let's look at some applied examples that bring this to life. For a university enrollment database.
We've used this example a bit, the problematic unnormalized design.
One giant enrollment, student ID, student name, major, course ID, course title, department, instructor, grade table, massive redundancy. Student name, major repeated for every course, course details repeated for every student.
Leads to all 3 anomalies?
All 3. It can't add a new course without a student. Deleting last student deletes course details, deletion. Changing major means updating many rows, update.
A mess.
So the normalized design separates this
into student ID, name, major, course ID, title, department, credits, instructor, and enrollment. Student ID, course ID, grade, semester. Each table focuses on a single concept, linked by primary and foreign keys, eliminating anomalies.
Changing a major is now one update in student. Tarleton can add courses easily.
Exactly. Builds a truly resilient academic system. Or an employee database.
Employee ID, name, dept, manager ID skill type. Manager ID is self-referential, showing hierarchy. Now, if we find skill type a bonus rate, a skill determines a bonus rate, and bonus rate is stored in employee.
That's a transitive dependency. Employee ID skill type bonus rate.
Right. To normalize to 3 and F, create skill type bonus rate. Skill type an employee becomes a foreign key, bonus rates updated in one place. Prevents inconsistencies.
Makes sense. How about a big e-commerce example like Amazon's vendor product order database?
Imagine a problematic unnormalized sales table, mixing order date, customer name, product name, vendor name, quantity.
Extreme redundancy, right? Customer name repeats, vendor name repeats.
Terrible. Leads to severe update anomalies. Changing a customer address means updating potentially dozens of sales records.
So the normalized design, many tables,
separates into logical entities. Customer, vendor, product, order line. Each entity gets its own table. Vendor ID in product is FK to vendor. Customer ID in order is FK to customer.
And order line links orders and products.
Right. Order line. Order I, product ID, quantity. Order ID day and product ID form a composite PK, linking specific products to specific orders. Now, updating a vendor's name is one change in vendor. Amazon can add new products or vendors easily.
Ensures consistency across billions of transactions. Makes complex stuff like order fulfillment efficient.
Which is why normalization is a cornerstone of enterprise systems.
Okay, we've talked about designing and organizing data, making it clean with normalization, but how do we actually talk to these databases? How do we ask them for information or tell them to change something?
That's where query languages come in.
These languages allow users to request information. Two types, right? Procedural and non-procedural.
Generally, yes. Procedural languages require you to specify step-by-step instructions on how to get the data. Non-procedural languages let you describe what you want, and the system figures out the steps.
Okay. Where does relational algebra fit in?
Before we seek SQL, let's truly understand the grammar of the database world, its foundational logic. Relational algebra is the procedural language that underpins everything. It's a formal system that takes one or two relations, tables, as input, and produces a new relation as its output.
Works on whole tables, not row by row.
Importantly, yes, which is a powerful abstraction and crucial for understanding what goes on behind the scenes when you write a query.
What are the main operations? Set operations first.
Its fundamental set operations are familiar from mathematics. Union, U, intersection set difference, and Cartesian product X. For union, intersection, and set difference, the tables must have the same number of columns and compatible data types.
Like depositor U-borrower combines all customer names.
Combines all unique customer names and SIGIs from both tables, providing a consolidated list, yes.
Okay, then the fundamental relational operations.
These are specific to relations. Select filters rows based on a given condition, like putting on a filter.
Price 500, book finds books, price to 500.
Exactly. Shows only rows meeting the criteria. Project. Selects specific columns, discarding others, and importantly, removes duplicate.
So title, book, lists all book titles just once each.
Correct. Without authors or prices, just unique titles. Renames. Simply changes the name of a relation table or its attributes, columns.
Pretty basic. Are there others?
Relational algebra also includes additional and extended operations. Natural join efficiently combines two tables based on common attributes without duplicating columns. Very common. There's assignment to store intermediate results, arithmetic operations, and crucial aggregate functions like SO, AVG, count distinct, max, MIN.
For calculating totals, averages.
Right. Computing summary values across sets of data.
Yeah.
And various outer joins, left, right, full, deal with missing information by padding results with NLLs.
So you don't lose data in joins.
Ensures no data is accidentally excluded during the join. This provides a complete set of theoretical tools to precisely manipulate and query relational data.
While relational algebra is the theoretical backbone, in the real world, the language we use every single day to speak to databases is SQL. Structured query language, that's SO1, right?
That's the one. It's the undisputed standard, and for good reason.
Why is it so dominant?
SQL is incredibly flexible, allowing for complex queries while also being relatively simple to learn. It's designed to optimize results.
Meaning it figures out the best way to get the data.
Yes, the most efficient way. It provides a high level of abstraction, so you don't need to know the physical storage details, and it can handle incredibly complex situations. A powerful tool.
Okay, when you write SQL, you use literals for values, like quotes for strings.
Right. Tamil Selvin for a string, 536 for an integer, 24.7 for a decimal, or maybe 2450430 for a date time. Specific formats.
And the commands fall into categories.
DDL.
DML.
Broadly categorized, yes. DDL, data definition language, for defining and modifying the schema, create table, alter table. DML, data manipulation language, for managing the data itself, select, insert, update, delete. DCL, data control language, for managing user permissions. And TCL, transaction control language, for managing transactions, ensuring integrity.
It also supports various data types, like varchar.
Yes, types like varchar for varying length strings, character for fixed length number, integer, float, and specific types for date, time, timestamp. Understanding these allows you to design and implement relational schemas using SQL effectively, hitting KO3.
Okay, basic SQL. What about advanced SQL features, like using it in programs?
Right, we often need to integrate SQL with traditional programming languages. That's where embedded SQL comes in. The SQL standard defines ways to embed SQL queries directly within general-purpose languages like C or Java.
Using special commands?
Typically, exec SQL statements or maybe hashtag SQL blocks mark these embedded queries. Before executing, your program needs to connect to the database.
Username, password.
Often, yes. And for result sets returning multiple rows, you declare cursors to iterate through the retrieved rows one by one. Crucial for apps needing database interaction.
Okay, what if the query isn't known beforehand?
Then there's dynamic SQL. This is for situations where the SQL query isn't known until the program is actually running. Immense flexibility. Instead of pre-written queries, your application constructs SQL queries as strings at runtime, maybe based on user input.
How does that work?
Commands like prepare compile the query string, and execute runs it, often with placeholders for value supplied at runtime, vital for tools like custom report builders.
And how do apps generally talk to any database?
Yeah.
Connectivity standards.
Crucial standards like ODBC, Open Database Connectivity, and JDBC, Java Database Connectivity, define APIs for this. ODBC provides a standard API for applications, regardless of language, to connect to any ODBC-compliant database. Think GUIs, spreadsheets using it. JDBC is specifically for Java programs, offering a similar API for Java apps to connect to database servers.
So they act like universal translators.
Pretty much. They abstract away the specific database details, allowing applications to communicate seamlessly with various backends. Lets your app talk to any database server.
Okay, so in any multi-user environment like Tarleton's registration system or a big e-commerce site, a significant challenge arises. Multiple transactions trying to access and modify the same data simultaneously.
Sounds like a recipe for conflicts.
Without proper controls, yes, it can quickly lead to conflicts and data inconsistencies, corrupting the very integrity we've worked so hard to establish. Imagine two students trying to enroll in the last seat of a class at the exact same millisecond. Who gets it? Needs control.
So we use database locking.
Exactly. Locking mechanisms are essential to ensure that only one transaction can modify a certain piece of data at a time. Two main types. Exclusive locks, write locks, prevent others from reading or modifying the locked resource during a write. Ensures data isn't corrupted during an update.
And shared locks, read locks. Allow multiple transactions to read the locked data simultaneously, but prevent any write operations until all shared locks are released. Balances concurrency with consistency.
Can you lock different amounts of data? Locking granularity.
Yes. Locks can be applied at different levels. Row-level locks offer fine-grained control, high concurrency as only the specific row is locked. Table-level locks are simplest, but lowest concurrency, the whole table is locked. Page-level locks strike a balance, locking entire blocks of memory.
Pages. And there are different philosophies for applying locks. Concurrency control approaches.
Two main philosophies. Pessimistic concurrency control assumes conflicts are likely.
So it locks things up front.
Yes, locks are used up front to prevent conflicts before they occur. Ensures consistency but can reduce performance due to lock overhead. Optimistic concurrency control, on the other hand, assumes conflicts are rare.
Lets transactions go ahead without locks initially.
Right. Transactions proceed without locks, and checks for conflicts only happen before committing. If a conflict is detected, roll back or retry.
Faster if conflicts are rare, but less reliable if they aren't.
Exactly. Improves performance in low contention systems, but less reliable in highly contested environments.
A critical issue with locking is deadlock, right?
Yeah.
Transactions waiting for each other.
Yes, a vicious cycle. Two or more transactions end up waiting indefinitely for each other to release locks. Complete standstill. Imagine. Transaction A locks resource 1, waits for resource 2. Transaction B locks resource 2, waits for resource 1. stuck.
How do systems fix this? Resolution.
DBMS employ several strategies. Detection mechanisms periodically check for deadlocks and abort one transaction to break the cycle. Timeouts automatically roll back a transaction if it waits too long. Or building wait for graphs to visualize and detect circular waits. It's a constant battle in busy systems. Selecting the right RDBMS relational database management system is one of the most critical business decisions an organization makes. Directly impacts goals, KO4, SO3.
Not just technical, but strategic.
Absolutely. Requires careful balancing of technical and financial factors for current and future needs.
What's top of the left? Performance.
Firstly, performance and scalability. Can it efficiently handle complex queries, manage massive datasets, cope with high transaction volumes? Look for query optimizers, indexing, scaling pathways, vertical and horizontal.
Then data integrity and reliability. ASIC compliance.
Non-negotiable. Full ASIC compliance, robust backup recovery, fault tolerance through replication, clustering for high availability, prevent data loss.
Security features must be crucial too.
Paramount. Strong authentication, authorization like role-based access, data encryption at rest, in transit, comprehensive audit logging for tracking and compliance.
How well does it speak SQL support and query optimization?
Key. Does it adhere to standards, offer advanced optimization, stored procedures, triggers for automation and business logic?
And advanced features to look for.
Things like foreign key constraints, full-text search, partitioning for large tables, maybe even NoSQL integration for semi-structured data.
What about managing it? Ease of use and administration.
Shouldn't be underestimated. An intuitive GUI, automation for routine tasks, clear documentation can significantly reduce administrative overhead and costs.
Speaking of costs, cost of ownership.
Goes far beyond initial licensing. Includes ongoing maintenance, hardware, training, operations. Open source might seem cheaper initially, but may need more internal resources.
Support matters too. Community and vendor support.
Vital. For open source, an active community is invaluable. For commercial, look for clear service-level agreements, SLAs, and responsive support.
And does it play well with others? Compatibility and integration.
Crucial. With existing infrastructure, OS, languages, frameworks, BI tools, needs to fit into the ecosystem.
Lastly, the cloud. Cloud and hybrid deployment.
Increasingly important. Does it offer managed services on AWS, Azure, Google Cloud? Can it operate in hybrid environments? Strategic questions guiding selection.
Okay, we've spent a lot of time championing normalization, essential for data integrity. But in the real world, designers sometimes intentionally introduce redundancy. Denormalization. Sounds completely counterintuitive. Why undo all that meticulous cleaning?
Denormalization is a very calculated move, a pragmatic trade-off usually undertaken to significantly improve database performance.
Performance, how?
Especially for read-heavy applications like data warehouses or systems running complex real-time analytical queries. In these scenarios, a fully normalized design with many small tables requires numerous joins to get the full picture, which can significantly slow down queries.
So denormalization reduces joins.
It can dramatically simplify queries by reducing joins. It often consolidates related data into fewer, larger tables, making retrieval much, much faster.
But there are risks, right? Reintroducing problems.
Significant risks, yes.
Yes.
You knowingly reintroduce increased storage requirements and, crucially, the potential for those insertion, deletion, and update anomalies we work so hard to eliminate. Data consistency becomes harder to guarantee, requires meticulous management.
So it's a deliberate, careful choice. Strategic use.
It's almost always a decision made after a normalized design is achieved and thoroughly understood. Not a shortcut for poor design. It's a pragmatic decision to optimize for specific critical performance bottlenecks. Mitigation strategies, like careful application logic or database triggers, are then put in place to manage and minimize potential anomalies.
So normalizing your database is silly. Sometimes, maybe.
As some might provocatively suggest, yes, in certain contexts, but only with a full understanding of the trade-offs and how to prevent the pitfalls. It's about informed compromise. #outro.
Wow. From Codd's revolutionary idea that transformed how we think about and manage data, to the meticulous steps of normalization that expertly fight off those pesky anomalies, we've seen how the relational model provides a clear, robust framework for database design.
Making sure our digital world runs smoothly and reliably.
Keys connect our data, constraints keep it impeccably clean, and normalization ensures your data is trustworthy.
Indeed. Every time you interact with a digital system, whether you're logging into your Tarleton student account, checking your bank balance, or streaming a show, you're engaging with these carefully constructed foundations. The ability to design design, develop, and secure these systems isn't just a technical skill, it's a foundational capability. It will serve you incredibly well, whether you're analyzing business data, working to safeguard patient records in healthcare, or building the next big app in e-commerce.
So keep exploring, keep questioning, and keep digging into the data. If you enjoyed this deep dive, please follow and share. All the resources we mentioned are in the episode description.
And think about this. If databases, the silent workhorses of our digital lives, were to vanish tomorrow, what parts of your world, from your studies to your social connections, would stop working first?
Something to ponder. Behind every login, every swipe, and every purchase is a database making it possible. Until next time, keep exploring the world behind the data.